Thank you, Nopparat. Very happy to be here this morning. Yes, I would like to start my presentation to introduce my research group because they are the intelligent people who are behind all this, what I'm actually trying to explain you. So I would like to especially um, um, stress the importance of our university researcher Omid Abdi and postdoc Mia Chumao's role in creating this deep learning things I'm going to present. And that I will not forget to mention our projects, the funders. The important to notice that we are the things I'm going to present you are based on the three important research projects. Two of them are funded from mostly from EU resources, and one is from Finnish sources. And then also what I want to also stress here is that in order to do this kind of AI work, like machine learning, deep learning, first of all, you need a lot of computer power working with images. And in our research group, we are having three special workstations with special GPUs, but also the biggest and most demanding computer calculation. You have to get more power even, and we have access to the national IT center where we utilize supercomputer infrastructure, and it's not actually very demanding. We have even student projects that we have been employing this kind of supercomputer power. So it's basically the same thing that with normal computers, but in larger environment. And then another thing I want to stress that in doing this kind of deep learning research, you need a lot of training data, and you need a lot of ground truth data also. So you need to have something that go to forest and say that this is a tree and this kind of soil type we have, or here are the year rings of the logs, and we have, of course, we have the pleasure of having so many excellent students carrying on the field works in our research projects. And of course, all the data need to be, you need to have exact position, RTK, GNSS system that are giving you high accuracy position. Okay, before I go to all those different recent our research projects, I will start a little bit larger overview and maybe a little bit back to what Ulla just said. And I have been recently asked many times that what is AI doing in forest operations, and even claims that it will change everything. And if we are looking at the basics, what is really happening in forest operations, I would say that AI will not change the foundations, but what we see now. So I would say that we have heavy logs. They are very, very heavy. We still means machines. We need engineers to design machines. We need to have machines to carry the logs to the roadside, and we need some vehicles to transport them to the industry. So that kind of basic thing is not changing. And I still believe that in forest, we need human expertise in silviculture and ecology. So we have to understand how forests regenerate, and what are the environmental impacts of forest operations. If we We cannot let AI to decide everything we do in our forest. And we know that in science we have very much contradictory cases that even scientists are not agreeing on different things. And at least we need humans to give values on what aspects should we prioritize. But then what AI will definitely change, it will change fundamentally how we perceive, understand, and operate in environments. So what actually Ulla just explained that we will in the future we can detect all the single trees and forest features. We can better understand and predict soil properties, and we can have optimal logging train network designs and things like that. And the development stages are listed here, as I think Ulla just mentioned, that we develop models how to detect different features, and behind that comes the understanding and operator support, even continuous operator support. And after that comes our automatization, robotization. And what AI will also do, it will definitely accelerate research and development processes. It will accelerate planning and proposal writing, data analysis. It's amazing what these things can do. For example, I have been a historically heavy user of Excels and making my graphics with Excels, and during the last couple of months I have changed it totally. So AI generated systems can do all these kind of things for you. You just let the code do everything, and you let the code to do your visualizations, and so these kind of processes are changing rapidly. And of course, we know that in writing, especially in cleaning your writing, you can benefit of those systems. But what remains that is important in using AI, I think we still need a lot of ground truth references, and we need annotations, labeling of reference data. That's still the thing that we need to leave for humans. I would say that this labeling work is there are progress that it's coming easier and easier, but in many cases it's still we need humans to do that. And then of course we are giving teaching at the university, and we have to ask frequently what is happening right now, and should we change the teaching to some extent? And we know that in forestry we have very strong tradition in statistics and in statistical modeling. And what is this machine learning then actually? I would say that we still need statistic and statistical model. They have a very important role. I think the experts in the future they have to understand the basic principle of statistics: sampling, variation, bias, uncertainty, and we need statistical modeling. So machine learning is more or less kind of add in layer that comes after that, and so when we are getting a large number of data, then we can benefit of machine learning. In forest operations, I think the first things I was working was when we have the idea of how to predict productivity of logging operations, and we have these harvester production files or MOM files, or we can even detect campus data from harvesters. This kind of data is coming automatically, and this is maybe the first steps we can employ the machine learning approach. I have to admit that when I was working the first time with machine learning, I was not so excited about that. I noticed that if you are having huge number of variables, there is always a huge risk that with your huge data sets, it's working and you can get models, and you can say that you will get better models that with the statistical regression models. But when you are then moving your model to a totally new environment, will it still work? So the problem with machine learning is that it's very easy to make it overfitting. So it will not work so well in other environment. Then I move more to this individual tree detection, because I think it's the most important steps in forest. When we go to the forest, I think that we can detect individual trees, and we have been mostly working in detecting trees from remote sensing data. And I guess the first steps in individual tree detection was, for example, trying to define from your remote sensing data, is this tree a certain tree species? Is this a pine, spruce, or birch? And we had LiDAR data, and you can then create a machine learning model, because you have a lot of data coming from remote sensing systems. With the first systems, you still need a human to do the feature engineering system. So humans were the ones who defined that, let's take this crown shape LiDAR variable, and this and this, and my screen disappeared for a while. And then with this machine learning system, you were able to get much more variables, and then you created the model with the machine learning algorithms. You separate your system to training and validation data, and you will create the model. But the challenge is the overfitting, and I have read many articles where you have a comparison between the classical regression model and machine learning model, and there are a slight increase in accuracy, but not it was not a breakthrough, this first step of machine learning. But the next step, deep learning, certainly is a breakthrough. So with deep learning systems, it's an idea where you can fuse different layers from different sources. For example, in our case, we have utilized LiDAR data, we have used optic images, and we have used multispectral images. And the basic idea with deep learning is also that it's not the human that is generating those features. The system algorithms do that by yourselves. So it's a training system which start to go around the data, and it will use different layers for utilizing the strength of the images, strength of the LiDAR, and strength of the multispectral images. For example, in detecting tree species, LiDAR is not that good, but if you take images and colors, and especially multispectral images, it brings you much more value. And with all those data labels, then you can train models that will detect the trees in a better way. And of course, this requires large number of training data and substantial computational power. Another slide trying to explain the idea what these deep learning models do, that they are not only doing the original data sets, they are also they can be taught to do changes in image resolutions. So if you have the original image like 256 by 256 pixels, so you have quite high resolution where you can detect even large branches. When you do resize the image resolution to half them and even make fourth of that, and then it comes to complete the image will change, and with lower resolution you can detect chrome shapes and so on. So all those layers are come together, and then it's actually kind of a logistic regression system where you try to find the solution and the best fit where with these kind of data structures you will have the best model to find the tree species you want. So with our project, we have been able to create models that with drone-based data, where we have a high accuracy LiDAR data, 30 to 40 hits per square meter, and image resolution something like 5 centimeters. We have managed to create excellent models that detect individual trees and define the tree species, define the tree heights, and then with the other model you can define the volumes and diameters at breast heights. And once you have this kind of tree map, you can do a lot of different things in forestry. You can identify trees and tree groups that are important for biodiversity. If you know the vertical and horizontal structures of the forest, you can think about the different management alternatives. Do we have an uneven forest structure in our forest or not? We can do different clustering work. Is there some area that we would like to manage the forest in different ways? All that logging trail network planning can be based on these structures we have in forest. And we can guide forest harvester operators in many ways, which we know the tree maps exactly. So we can ask, is this the future? Even that before we go to the forest, we have a complete description of the trees. Shall we create a digital twin of forest? Shall we do the operation before we go to the forest in our computers and assist the operator into the execution of the operation? Another thing that we have also been working that now the first step we were working with very high accuracy data, and we ask ourselves that what can we do with open source data? In Finland, we have a luxury that the Finnish forests are LiDAR scanned every 50 years. So it means that we have a LiDAR coverage with 5 points per hectare, 5 points per square meter from all our forest, which means that we have and our images from those forests, they are roughly 50 centimeters. So in the left-hand side, you have two different images. The 5 centimeter data is the drone data, the best available, and the open source data looks like the lower one, 50 centimeter accuracy. But Zhu Mao in our group, she has been working with this kind of super resolution processes with the data. So we all remember those science fictions from early 2000 with Mission Impossible, where they use satellite imagery to reveal car license plates. So in forestry, this is coming a little bit possible today. So Zhu Mao has been able to sharpen the original data with AI from 50 centimeters. I didn't put the right number there, but the bigger image with the right hand side, it's the accuracy of 12.5 centimeters. So you can increase your resolution, and we have noticed that with the drone imagery plus LiDAR, we can detect trees with 60 to 90% detection accuracy. And with the dominant and co-dominant tree layers with almost 90% accuracy. And with this open source imagery and LiDAR in dominant and co-dominant tree layer, we can detect the trees with 70 to 90% accuracy. So what has happened in our research project? So when we have a system to use open source data, we can always, when we go to the forest, we can take this open source data and create the forest before we go to this is an example of our optimal value forest that we harvested. So we had even the tree map before we went to the forest with open source data. Okay, then I moved to another totally new area, and it's prediction of soil. And we know that this soil is very crucial in forestry, and we usually have rather poor information and understanding what kind of soil type we have. So we are not specialists in geomorphology, but we have been reading the articles, and we have in our system, we have employed this very famous so-called Skorpan model. So it's the system that try to explain the idea, what is actually, what is the history of this soil. And we according to this model, the soil attributes can be explained by these 7 different variables, like other soil properties, climate, organism, relief, parent, time, and spatial position. Of course, when we are in Finland, in certain region, we have the same climate, and usually we have the same parent material of the soil, and then we cannot do anything for the time. But regarding the vegetation that is growing on the soil and relief, the topography we have, and the spatial position, they are the ones that we can use in making prediction of the soils. So we have collected huge number of soil data, taking soil samples. We are analyzing the organic layer thickness about the mineral soil, and then we take the mineral soil sample, and we have a laser diffraction system at the University of Helsinki where we can detect the exact particle size distribution of those soil samples. And with that, we have collected from Western Finland, we collected from roughly 50 sites, more than 300 soil samples. And we have detected the vegetation above and delineated this kind of small areas in forest. And with aid of this deep learning system, we have managed to make predictions of those soils. And here are the list of the covariates that we have investigated. So we have a geomorphometry-based, so LiDAR-based systems related to geomorphometry, hydrology and trees, and then we have from Sentinel-based systems, we have different kind of vegetation indexes and soil indexes. And based on all those data and work with AI, we have managed to find out what is the importance of those different variables. And we can say that something like 50–60% is explained about your terrains and your topographical features. But the vegetational indexes and vegetational characteristics have also important role. So we have recently published this paper and it shows that we can make prediction of soil properties with very high accuracy and create excellent soil maps where you can predict the particle size distributions of the soils. And now we are working also with soil organic layer thickness and soil organic matter paper that is recently submitted, and we are also going to try to integrate these models with nationwide coarse scale maps in the future. Couple of years earlier also we worked with one important with the optimal logging network design, and the first step was to detect all trees we have in forest. And I think it's important that first step in this network design that you try to find out what you already have in forest. And this also needed a lot of training data, and actually we digitized all maps and find those old trails, and we developed models to that how we with remote sensing data with high accuracy LiDAR we can detect all logging trace. And with the recent work we have also linked that with the ruts we are having with the old logging trace. So it's important part also, and actually this part of work is recently largely adopted by practitioners. So we in Finland with certain manufacturer you can get maps for all over Finland that you can have all logging trace mapped before you go to the forest. This is actually the same thing with another little bit more complicated figures. Let's skip that. Last thing I would like to also show you and demonstrate is the latest work we are doing with value chain optimization, and so I would like to start with that figure in the middle of this slide. So I try to explain that we know that in northern countries, especially, most of the sawmills have a log tomographic scanner in log sorting line, and then they have a lot of AI in and machine vision systems align the processing lines. And we have machine vision systems to detect the knots of the boards. And they have detected this kind of AI system within the sawmill that if you detect the board later after drying process, you can then track it based back to the lock where it was actually processed, that board. So basically, if you sell a board, then you can trace back to the lock in the lock sorting line. So we are asking the question, can this same system and idea then be transferred to the forest also? And what benefit that could then do? So we are examining and looking at the possibility. Would that be possible to have a harvester camera assembled to the harvester head? Could that be the information that we could later then link this log from forest to the log at the log sorting line? And of course, while we are today harvesters, we are also having these high accuracy RTK GNSS positioning systems. We can say that and define the exact tree where the logs have been processed. And is that in the future possible that the lumber you are selling, you can also explain in which exact place it has been growing in forest? So we have had a prototype that is not actually a harvester camera. It's kind of a prototype that mimics what could be the camera assembled at the harvester head. And we are having photos from those discs. Actually, we are having dual photographs that we can later work with the stereo images also. And then with our collaborator in Korkeakoski sawmill, so it was earlier UPM sawmill, now it's Versowood sawmill, and they are having Finnish fusion system added also with this kind of lock and vision system. With that system, you can take a photograph from both ends of locks when you are arriving to the sorting mill. So we are now developing models. Can we detect individual tree rings? So it's also work that is you actually need a system. You have to have a human that will digitize every ring from your training data. We are digitizing annual ring of those training logs, which means that this digitizing work takes roughly 1 day of one log. So we cannot get huge amount of data, but we are doing our best. So it's extremely boring and time-consuming work. But with those systems, we are labeling the data. We are now working with these systems to make predictions of those annual. Can we detect annual year rings? And then we also work with matching the lock ends. So we know that from harvester, the lock ends are fresh, and usually at the sawmills, they are aged a little bit, they are dirty. So is that possible to then match these fresh logs and coming from a little bit not direct angle with the logs at the log sorting line? And also we are working with the photographs at the sawmill. So if you have all the logs from one forest, is that possible to match the logs from the same stem in the forest? So can we match the log 1 and log 2 from the same stem. So that's the area we are also working. Okay, that was kind of a large overview of what we are doing in our research project. So hopefully I didn't use too much time for this, and we still have time to discuss. Thank you.